Hello and welcome to our lecture on the chi-square goodness of fit test. Our EQ for today is how is goodness of fit test different from a chi-square test for independence. So before we get started, let me ask you this. Have you ever opened a pack of Skittles and gotten none of your favorite flavor? Then you exasperatedly exclaim, "Ugh, this always happens. I never get my favorite flavor." Well, if you wanted to compare what you actually get or observe in a Skittles pack compared to what you're supposed to get or expect, then you are performing a chi-squared goodness of fit test. This can see if a distribution of a categorical variable follows a claimed distribution. If the percentages of each category are substantially different from what is actually claimed to be true, then you have statistically significant result, and you can reject your null hypothesis. Let's try and put it a little bit more explicit to our mathematical language here. A chi-square goodness of fit test tests a null hypothesis that says a categorical variable has a specific distribution, i.e. your first proportion is equal to the second proportion is equal to the third proportion. Basically what that's saying is that all of your proportions or categories are going to be equally likely to occur. So in the context of Skittles, you're just as likely to get strawberry as you are green apple, as you are to get grape, lemon, or orange. But sometimes we know that there's actually a different distribution, that it does follow a specific distribution, but not necessarily that they're all the same. For example, M&Ms tend to have about 25% M&Ms blue, but only about 16% of them orange and like about 12% green. This is something that, for whatever reason, through market research at one point in time, M&M Mars Company decided this is the distribution we want to make our M&Ms in. So it might follow a distribution like that, such as the first proportion or the first category is going to make up 50%, the second category is going to make up 22%, and the third category is going to make up 28%. Now, of course, this all doesn't have to be done with candy. We can look at this and see population distributions based off of ethnicity or based off of gender, handedness, certain abilities or disabilities, something like that. There's tons of different ways that we can utilize a chi-square goodness of fit test, but one key thing is that we are only looking at one variable. When we are doing that, we are comparing an observed count to an expected count, assuming that expected count is true. So essentially, we are asking ourselves, how likely is it that we get these observed counts, or something even more extreme, when we assume that the expected count is true for the entire population? To perform a chi-square goodness of fit test, you follow the same four procedures. We write out our null and alternate hypothesis, that's step 1. You calculate your chi-square test statistic in step 2, and then you find your p-value. And if you're using a calculator, that's all done at the same time. Step 4 is to compare your p-value to alpha, a significance level, or chi-squared to a critical value. A couple other things to note with this: to calculate your degrees of freedom, that's just categories minus 1, no row total times column total, because essentially we're only going to have one row or one column because we only have one variable in a chi-square goodness of fit test. To be valid, though, it's the same conditions that we have seen in other significance tests so far. All expected counts must be greater than 5, and your sample must be unbiased or random. So for this, what we are really trying to say is that, did you take a large sample? That's ultimately what we want to know. And here we're collecting unbiased data. Again, one big thing to note that this is for one categorical variable. That's when we use the chi-square goodness of fit test. Okay? When we were looking at the chi-square test for independence, we were looking to see if two variables were independent of each other. Now we don't have that two-way table, we have a one-way table, okay? Because we are only looking at one categorical variable. Now that variable is likely to have several different categories, and we go about doing it a different way, but still it's one variable and one variable only. So one categorical variable for a chi-square goodness of fit test. Let's get into it by doing an example. Alright, it's time to show Skittles who's boss. The Wrigley Company, the makers of your beloved rainbow treat, says the distribution of flavors in the original Skittles is uniform. That's a huge component right there, uniformity. Meaning there are the same proportion of strawberry, lemon, orange, green apple, and grape Skittles. You happen to think otherwise, so you orchestrate a small-scale test with 30 bags of Skittles, open them up, and count the rainbow. Below are your data. So we've got tons of Skittles to choose from all of our different flavors. But the first thing that we need to recognize is still, even though there are 5 flavors, there's still just one variable. So that's going to help us understand how we are going to approach and analyze this statistically. And it is a categorical variable. So again, the difference between categorical and quantitative is really important, and knowing how many variables we have, super important when we're trying to decide upon specific significance tests. We need to conduct an appropriate statistical test at the alpha equals 0.05 significance level to refute the claim that the distribution of Skittles is uniform. So, one categorical variable, we want to test to see is it uniform or not. So we're trying to see, is it following a given distribution? That means we are going to perform the chi-squared GOF test. Okay, so with that, now we know how we're supposed to write our null and alternate hypothesis. So we can write it out using the symbols. We could write it out like this, saying that the proportion of strawberry is equal to the proportion of orange, lemon, green apple, and grape. We could say that all of those are going to be equal to each other. Or we could do it verbally, right? We could do this verbally and just say the distribution of Skittle flavors is uniform. Now our alternate hypothesis is just one simply of difference or change, that at least one of these flavors does not follow this given distribution. Okay, so we could say at least one flavor follows a different distribution or follows a different proportion. At least one flavor has a different proportion. Or probably the more simple way is to just refute directly this claim and say that the distribution of Skittle flavors is not uniform. Probably the simplest way to do it. Just the same way that we did that two variables are not associated versus two variables are associated, right? Here we are saying the distribution of flavors is uniform. The other we're saying they are not uniform. They are different from each other. So one thing that we can do that's actually pretty simple and just gives us a little more evidence that we know what we're doing here is to actually find the expected counts of these. Now this is no different than all the statistics expected counts that you've been doing before. The first thing we need is the total. How many total Skittles do we have? Well, if we add all these up, you can double check me if you want, but we have 1,765 total Skittles, right? That was our grand total. Now the expected value or expected counts was always just E equals N times P, and really it's not any different here in this case when we're looking at just the one variable. Okay, when we're looking at one variable, the expected counts for each of these cells is super easy. So we have a total of 1,765, and each of them are going to have that proportion of 20% or 0.20. When you multiply that, if this is a truly uniform distribution, we will have 353 of each color or each flavor. So that means we have 353 here, 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 and here. And this will be our expected counts table. Okay, and it's really handy to have the expected counts right alongside your observed counts, because you can start to see component analysis where we can start to see which ones are going to, if we get a result, a statistically significant result, which ones are going to show the greatest differences in contributing to us getting that different result. And that's going to be really important later on. Now, we could find the expected counts, the expected value of each one of these to find the chi-squared. It's still going to be the sum of all observed minus expected counts squared divided by the expected counts. We could do that, do it all by hand, or we can just use a chi-squared GOF calculator, and we can provide our results. So let's find a calculator online to do this, and the same Sociostats website that we found before for our chi-square test of independence is going to be what we're going to use here. So here's my chi-square GOF calculator that I've found. You'll notice that it only is producing rows for you, just like what we would see on our table. So we have strawberry, orange, lemon, green apple, and grape. I typed those in already. If you need to have more rows, more categories, then you're going to have to find a different calculator, but this one will work for us just fine. Let's go ahead and click Next and see what we get. So now we have the option to type in our observed and our expected. Now we could do the expected counts, or we can do the expected proportions. You don't have to do both the same. I'm going to click proportions because that's just going to be a little bit easier. And I'm going to type in each of the proportions that we had from before. So I had 302 that were strawberry with a 20% expected proportion. I had 318 that were orange with, again, an expected 20%. Filling in the rest of the table here. And we can state our significance level as 0.0 or 0.05. You'll notice that 0.2 versus 0.20 is not going to make a difference. Click on the chi-squared test statistic and we will get our results. So we can see that it gives us the observed and it even gives us the expected counts right there. It even shows us the difference. It shows us the difference of them squared, and it shows us the difference of them squared divided by that expected counts. It does everything for us, even sums it all up, but it breaks down and even shows the work. That is pretty nice. 18.640, you see that in the bottom right cell as well as in the results sentence here. The chi-squared value is 18.64, and it gives us a p-value which is pretty dang small of 0.00092. So let's go back and actually write out our results. So here's our results. We had a chi-squared test statistic of 18.64, which if we round it to 3 sig figs is going to be 18.6. So there's our 3 sig figs. We had a degrees of freedom of categories -1. We had 5 different flavors, so 5 different categories that had degrees of freedom of 4. All of our expected counts were all greater than 5, as we saw, so that was valid. We can also assume that each bag was filled randomly. So that helps us say that we have something that is unbiased and random selection. And then we get finally our p-value. And our p-value was 0.00092, and that is definitely less than alpha. So our p-value is less than our alpha of 0.05. Hence, we reject the null hypothesis. The distribution of Skittles flavors is not uniform. We have statistically significant evidence that it does not appear, based on this very large sample, that the distribution is not uniform. Now, it might be pretty close, but it's definitely not uniform. At least that's what our sample of 1,765 Skittles happened to show. Now, could we have had bags that came from factories where the machines were not filling the bags very evenly? Yeah, absolutely, we could see that. Could we have had a defective machine that was actually pumping out too few red, too few of our strawberries, and too many of our grapes? That's certainly possible too. Okay, but based on this evidence that we see here, we have a statistically significant result to state that the distribution is not uniform. Alright, that's it. Thanks for watching, you guys. Have a wonderful day. I'll see you next time.